Hello friends, today is the fifth part in the chapter alcohols, phenols and ethers. Today we shall see the physical properties and chemical properties of phenols, because in our previous session we have studied about the methods of preparation, nomenclature, classification of phenols. Today we shall study physical and chemical properties. First, physical properties. The first physical property is always physical state. So, phenol is a colorless liquid, or sometimes it exists as a colorless solid at room temperature, depending upon the conditions. If the temperature is too cold, it exists as a solid, otherwise it exists as a colorless thick viscous liquid. Phenol, when it is in liquid form, it is thick and viscous. When it is in solid, it is highly deliquescent. Deliquescent means one which absorbs water easily. So, phenol at room temperature can exist as a colorless liquid or as a colorless deliquescent solid which can absorb water easily, and phenol has got characteristic carbolic odor or phenolic odor. Now, you may ask, sir, how do I know what is carbolic odor? It is the same smell that we find in Lifebuoy soap. So, that smell is called carbolic odor. So, the first property is their physical state. So, phenol is colorless liquid or colorless solid. What kind of solid? Deliquescent solid with characteristic carbolic odor. The second property, generally phenol is corrosive. While you are handling phenol in the laboratories, we advise you not to handle phenol with bare hands. Compulsorily use a test tube holder while you are adding phenol into test tubes or beakers, etc. The reason is phenol is highly corrosive and it causes blisters when dropped on skin. Your skin can show severe irritation and loss of skin upper layer. The entire part wherever phenol falls on the skin becomes entirely white. The cells become dead. For this reason, phenol is corrosive and it should be handled with care. It causes blisters when fallen or when dropped on the skin. The third property is phenol is sparingly soluble in water. It does not easily dissolve in water. But however, phenol is easily soluble or readily soluble in organic solvents such as ether, alcohol, sodium hydroxide, benzene, etc. But in water, it is sparingly soluble. When I say sparingly soluble, it means that it is not completely soluble. A part of phenol can be solubilized in water, but the rest of it remains as it is. If you want phenol to be soluble, then you should use organic solvents such as benzene, ether, sodium hydroxide, etc. And the last one, phenol boiling point is higher. Its boiling point is higher than that of corresponding aromatic hydrocarbons. Corresponding aromatic hydrocarbons refers to benzene. So, if you compare benzene with phenol, the boiling point of phenol is higher. This is because phenol shows intermolecular hydrogen bonding with its own molecules, like in this form. One phenol molecule is bonded to another phenol molecule by means of intermolecular hydrogen bonding. Because of this bonding, each phenol molecule exists in harmony with other phenol molecules. As a result, they keep bound. They are bonded to each other by means of intermolecular hydrogen bonding, making the boiling point slightly higher than those of aromatic hydrocarbons, that is benzene and other compounds. So, phenol has higher boiling point than other aromatic hydrocarbons. This is due to intermolecular hydrogen bonding. These were the four physical properties. The first was physical state. Phenol's physical state is either colorless liquid or colorless solid. It exists as colorless solids only when the temperature is too low. Then the smell of phenol is carbolic odor. The second was phenol is corrosive when dropped on skin, therefore it should be handled with care. The third is phenol is sparingly soluble in water but readily soluble in organic solvents. Fourth is their boiling point, which is higher than corresponding aromatic hydrocarbons. You also need to remember that sometimes phenol can be visualized in pink color. If you open a bottle of phenol, initially it will be colorless, but upon exposure to air, it can turn into darker shades like pinkish color, reddish color. This depends on the extent of oxidation that has took place. So, if you happen to see phenol in pinkish color, do not get confused that it is not phenol, because you have studied the physical property of phenol as it should be colorless liquid or colorless deliquescent solid. Yes, it should be like that, but if oxidation takes place, if air enters into a bottle of phenol, it can change its color from colorless to pink. So, phenol becomes pink only due to atmospheric oxidation. You need to remember these physical properties. The next is chemical properties. Second part is chemical properties of phenols. The first chemical property is acidity of phenols. In our previous sessions, we have studied the acidity of alcohols. We know that alcohols are acidic. Why are they acidic? They are acidic because they can easily donate a proton. On the same lines, phenols are also acidic. They are acidic because they too donate a proton. This can be seen by a reaction wherein phenol is reacting with an alkali metal like sodium metal, and this gives you sodium phenate or sodium phenoxide with liberation of hydrogen gas. For this to happen, you need to take 2 molecules of all. Now in this reaction, you have an idea that whenever phenol reacts with sodium metal, this hydrogen will be lost as a proton. Since 2 molecules are involved, therefore a molecule of hydrogen gas is lost. This reaction of a compound like phenol reacting with alkali metal, that is basic metal, shows that it is acidic in nature. Phenol also reacts with another compound like a base like sodium hydroxide to give the same product, sodium phenate or sodium phenoxide plus water. Now this second reaction, it implies that phenols are more acidic than alcohols. Sir, how do I say that? See, alcohols did not react with sodium hydroxide. Sodium hydroxide is a very strong base or a very strong alkali which did not react with alcohols. Alcohols fail to react with strong bases like sodium hydroxide, whereas phenols did react with sodium hydroxide. So this shows that phenols are more stronger acids than alcohols. Alcohols are weaker acids than phenols. Also, based on Ka values, for alcohols, do you know what Ka value is? Ka stands for dissociation constant. You should be aware of this concept from your first year equilibrium chapter. There you have studied what dissociation constant is. So based on dissociation constant values of alcohols and phenols, also you can be able to identify which of them is a stronger acid. Alcohols have a Ka value of 10 to the power of 18, phenols have 10 to the power of minus 10, alcohols 10 to the power of minus 18, phenols 10 to the power of minus 10, and carbonic acid has 10 to the power of minus 7. Now simply looking at these values also, you can identify which one is a stronger acid. Okay, so compared to alcohols, phenols are stronger acids. However, phenols are weaker acids than carbonic acids. This is because carbonic acid's Ka value is 10 to the power of minus 7. Understood? So alcohols are weaker acids. They are weaker acids because they do not react with sodium hydroxide and also based on their Ka values. Phenols are stronger acids than alcohols because phenols also react with sodium hydroxide along with sodium metal. Also, phenols Ka value, dissociation constant value, is higher than alcohols. However, phenols are weaker acids than carbonic acids. Also, there is another concept to explain how the acidic character or how the acidic strength of phenols depends on some of the groups attached to it. Before that, you need to understand some concepts of resonance which implies even to phenols. See, when you write phenol structure and its dissociation, imaginary concept, then you indicate this as phenate ion and H plus. Whenever phenol is able to dissociate and liberate this H plus as a proton, only then we say phenol is acidic. Now for this to remain as acidic, this reaction should take place compulsorily. Now when this reaction happens, this H plus should be gone. For this to go, we say the strength of an acid, the strength of phenol as an acid depends on the stability of this phenate ion. Larger the time phenol spends, as phenate ion, only then phenol will behave as an acid. Until and unless phenol remains as phenate ion, this cannot go. So if phenol is remaining in this phenate form, as long as phenate form is present, protons are present. So the strength of phenol as acid, phenol's acidic strength depends upon its ability to remain in phenate form or phenoxide form. Now you can ask, sir, how does this remain stable? That is explained based on the resonance structures of phenoxide ion. If this is phenoxide ion, negative charge implies surplus or extra electrons. So if these electrons are transferred to the carbon here, then carbon already had 4 bonds, so it will shift its own electrons to adjacent carbon. As a result, our next resonance structure will have these 2 bonds same as it is. Here oxygen, because charge is lost, oxygen has lost its electrons, it carries positive charge and it becomes double bond. The same electrons in the first structure came outside on the next carbon, that is indicated as a negative charge. In our next resonance structure, what happens? The same negative charge is transferred to another carbon and the same electron density is transferred to adjacent carbon. Hence, this structure. Here negative charge, double bond O plus. Again, the electron density is transferred. Therefore, our other structure will be here and here. Here negative charge, double bond O plus. This comes here. It again goes back to its normal position, giving our first final hybrid structure, that is 1, 2, 3 double bond O, single bond O, again a minus charge. Now as long as the electrons keep on delocalizing, as long as the electrons keep on shifting, this molecule, this phenate ion remains stable. As long as phenate ion is stable, protons exist, and as long as these two exist, phenol exists as an acid. Therefore, the acidic strength of phenol depends on its ability to exist as phenate ion. Larger the time is spent by phenol as phenate ion, greater will be its acidic strength. Now what happens if phenol is substituted? If anywhere, if phenol has got OH on it and if it has got any substituent attached on any of the 5 carbons, will it affect the acidic strength or acidity of phenols? Yes. So there are 2 kind of groups. One we call electron donating groups and the other we call electron withdrawing groups. So electron donating groups can be methyl, amine, etc. Electron withdrawing groups are those groups, those functional groups which contain multiple bonds in them, like aldehyde, carboxylic acid, nitro group, though it is not a functional group, etc. Now, what happens if a phenol is substituted with any of these groups? Let us first see electron donating group. If an electron donating group like methyl group or amine group is attached anywhere, say here. So, instead of this circle I will write alternate single and double bonds. What happens to the acidic strength if an electron donating group is attached? Whenever an electron donating group is attached, each electron donating group, by virtue of its positive inductive effect, it donates electrons. So, if it donates electrons, the electron density here increases. Understood? The electron density on the carbon increases. So, if it somehow becomes phenate ion, and if the same electrons are to be transferred here, this carbon will not accept the electrons as the nearby carbon atom is pumping its own electrons here. Understood? As a result, whenever electron donating group is attached to phenol, an electron donating group increases the electron density on benzene ring. It increases the electron density on benzene ring. Whenever electron density on benzene ring increases, it cannot accept electrons from oxygen attached to it. When it cannot accept electrons by oxygen, this oxygen again goes and binds with hydrogen and becomes phenol. So, the acidic strength decreases when an electron donating group is present. If an electron withdrawing group is present, say if the same phenol is attached with an electron withdrawing group like nitro group. Nitro group, by virtue of its negative inductive effect, withdraws electrons. So, here you have less electron density, the electron density here decreases. So, benzene ring can easily accept electrons donated by oxygen. The same electrons can be easily transferred to this carbon. This happens when benzene is substituted by electron withdrawing group. So, if an electron releasing group or donating group is attached, the electron density on benzene ring increases. This decreases the stability of phenate ion. Higher the stability of phenate ion, greater is the acidic strength. Therefore, presence of electron donating group decreases the acidic strength. Presence of electron withdrawing group increases the acidic strength of phenols. Now, second property. The second property is esterification. You have already studied esterification in alcohols chapter, but still phenols also show esterification reaction. How? Whenever phenol reacts with carboxylic acid, I will write it reverse. Then you have esters. So, this reaction is called esterification. Whenever phenols react with carboxylic acids, then you are likely to get esters. One typical application of this reaction is used in preparation of a drug called aspirin. In order to prepare aspirin, you need salicylic acid, that is this compound. 2-hydroxy-benzoic acid is called salicylic acid. If salicylic acid is acetylated, if it is acetylated by using acetic anhydride, then carboxyl group remains unaffected, whereas the phenolic group becomes esterified. Therefore, this compound is called acetyl salicylic acid along with formation of acetic acid. Acetyl salicylic acid is commonly called aspirin or ASA. It is called aspirin or ASA. Aspirin is a very good compound used as a painkiller, as an analgesic, especially during heart strokes, birth time, labor pains, etc. It is a very good drug. So, you can expect this as an important question during exams, as how do you convert salicylic acid into aspirin. It is one of the applications of esterification. Then the third chemical property is electrophilic substitution reaction. Just now we saw the resonance structures wherein the negative charge appeared only at ortho and para positions. So if you bear this in mind, then studying of electrophilic substitution reaction becomes easier. An electrophile is anything that carries a positive charge. So in phenols, the electrophile is hydrogen that is attached to the 5 carbons, any hydrogen attached to the 5 carbons. So if you want phenol to be substituted by any electrophile, then either this position or this position, that is ortho and para positions, are preferred. It is because the electrons are more at these 2 positions only, and electrophile being electron deficient, they attack these 2 places only. So the first one is nitration. In nitration, when phenol is reacted with dilute nitric acid at about 20 degrees Celsius, then you will get 2 products. One is here and the other is, one is para and the other is ortho. One is orthonitrophenol and paranitrophenol. Now these 2 isomers, orthonitrophenol and paranitrophenol, they exist as a mixture. Then how do we separate them? So you can separate them by means of a method called steam distillation. This is a 1 mark question, sometimes asked in exam. It has been asked twice or thrice if I am not wrong. As how do you separate a mixture of orthonitrophenol and paranitrophenol? It is done by steam distillation. How is it done by steam distillation? It is because of this compound which is steam volatile. It is steam volatile because of formation of intramolecular hydrogen bonding. Because of intramolecular hydrogen bonding, ortho isomer is steam volatile, whereas para isomer is not. Para isomer has got intermolecular hydrogen bonding, by virtue of which its boiling point is higher than that of ortho isomer. So if a mixture of ortho and paranitrophenol are there, and if you want to separate them, steam distillation is the best method, because ortho isomer is steam volatile whereas para isomer is not. So whichever comes out of the flask is, first is ortho isomer followed by para isomer. Whose boiling point is higher? Para's boiling point is higher. If during nitration you do not want to use dilute nitric acid, if you use concentrated nitric acid, in other words, if you use nitrating mixture, that is concentrated nitric acid in presence of concentrated sulfuric acid, then you get this compound. You get 2,4,6 trinitrophenol. You get 2,4,6 trinitrophenol. 2,4,6 trinitrophenol is also called picric acid. It is called picric acid. This question is also important in exam. How do you convert phenol into picric acid? Question mark, give equation, again question mark. So it's a 2 mark question. How do you write? Whenever phenol is reacted with concentrated nitric acid in the presence of concentrated sulfuric acid, you get picric acid. 1 mark for the statement and 1 mark for the equation. After nitration we have halogenation. Under halogenation, especially bromination. So how is halogenation done? During halogenation, if phenol is reacted with bromine water, then you get then you get 2,4,6 tribromophenol. You get 2,4,6 tribromophenol, which exists as a white precipitate. If the same reaction is carried out with bromine in presence of an inert solvent like carbon disulfide, then you get two isomers. One is ortho and the other is para. So, if you use bromine water, more ionization takes place, therefore 2,4,6 tribromophenol is obtained. If the same bromination is done in carbon disulfide, two compounds orthobromophenol and parabromophenol are obtained. This was electrophilic substitution reaction. Three chemical properties are done. The fourth chemical property is a named reaction called Kolbe's reaction. In the previous session I have already told you that alcohols, phenols and ethers is an important chapter because there are many named reactions, there are many important reactions that are appearing in almost all competitive exams and even in your theory exams. So, Kolbe's reaction is one of such important reactions wherein phenol is reacted with sodium hydroxide. Now, you should know what the product is obtained. The product is sodium phenate or sodium phenoxide. So, sodium phenoxide or sodium phenate is our starting product and not phenol. So, if they ask you in exam what Kolbe's reaction is, you are not supposed to write Kolbe's reaction is starting from phenol, begin with sodium phenate. So, in Kolbe's reaction, whenever sodium phenate is reacted with carbon dioxide, when it is reacted with carbon dioxide at a temperature of about 140 degrees Celsius under 6 to 7 atmospheric pressure, then what happens? See clearly, here one hydrogen is present. Imagine you are removing that hydrogen, attach it here, OH here. The same hydrogen is transferred here and this COO here, Na is transferred here. This compound is obtained which is called sodium salicylate. Most of the times students get confused, sir, where did this hydrogen come from? So, except this carbon, all the 5 carbons have got one hydrogen each. You select any one carbon, I will select from here. The same hydrogen is transferred here. Carboxyl group is attached here, followed by sodium group. So, sodium salicylate is obtained, whose hydrolysis will give you salicylic acid. This reaction is called Kolbe's reaction. What is Kolbe's reaction? Whenever sodium phenate is reacted with carbon dioxide at a temperature of 140 degrees Celsius under 6 to 7 atmospheric pressure, sodium salicylate is obtained whose acidification gives salicylic acid. This reaction is called Kolbe's reaction and it is a named reaction, important reaction for exams. Then our fifth chemical property is another named reaction, again a very important question. It is called RhymerTimon reaction. RhymerTimon reaction. These two scientists, Rymer and Timon, they gave you this reaction. I will first write the entire reaction. You see if that is easy, follow that one, or else we have a condensed reaction also. So, in this reaction, you react phenol with sodium hydroxide. It becomes at 60 degrees Celsius, it becomes sodium phenate. It becomes sodium phenate along with water. Now, in the second step, take that sodium phenate, and react it with Chloroform. Chloroform is CHCl3. Instead of writing in this form, I will separate one chlorine and attach here. Okay. Then here ONA as it is. Here was one hydrogen. You eliminate that hydrogen with chlorine. If that is gone, you will have HCl. What is left behind? Here CH, 2 times Cl, once, twice. The same Cl2 I have split. In the next step, here ONA, here CH, Cl and Cl. To eliminate these two chlorine, you add 2 molecules of sodium hydroxide. So this part will be gone. 2 NaCl is lost along with here ONA, here CH, OH, OH plus 2 NaCl. Now, I reminded you, I have told you in the last class that 2 hydroxyl groups should never be attached to one carbon. It will become unstable. On that note, if 2 OH are attached to one carbon, you eliminate one water molecule. Then, with the loss of one water molecule, you will have sodium salicylaldehyde. You will have sodium salicylaldehyde. If this sodium salicylaldehyde is now hydrolyzed with an acid, then you will have OH CHO plus NaCl. This compound is called salicylaldehyde. So what is RhymerTimon reaction? RhymerTimon reaction is conversion of phenol into salicylaldehyde. If this method is easier, follow this one. Otherwise, you can condense this reaction as, whenever phenol reacts with sodium hydroxide and chloroform at a temperature of 60 degrees Celsius, you will get salicylaldehyde. You will get salicylaldehyde as a product. Now, simply writing this will not get you the entire marks because it is a lengthier question, a 3-mark question. You need to write the equation in balanced form. So notice here, once sodium hydroxide, again twice, so total 3 times. So when phenol reacts with 3 moles of sodium hydroxide and 1 mole of chloroform at 60 degrees Celsius, salicylaldehyde is obtained. Along with this, what are the byproducts? Water once plus HCl once, NaCl twice, again water means 2, again NaCl means thrice. Understood? On that side, sodium hydroxide once, twice, thrice, and HCl once. So HCl once I wrote here. Here HCl and here HCl get cancelled. So what remains is this, plus 3 NaCl. So if you write this equation in balanced form, then it is correct. Otherwise, follow this method. Follow whichever is easier to you. This is not the only RhymerTimon reaction that is given in the book. There is also one more RhymerTimon reaction. For those who are concentrating only on theory part, practice only RhymerTimon reaction which gives you salicylaldehyde. For those who are practicing for all other competitive exams, you need to study the second RhymerTimon reaction, which is this. In the second RhymerTimon reaction, the first reaction remains same for giving sodium phenate. In the second, instead of chloroform, we use carbon tetrachloride, CCl4. So instead of CCl4, I will write CCl3 and 1 chlorine here, which gets separated. So you will now have 3 chlorine atoms. In the next step, before there were 2, so you used before there were 2 chlorine, so use 2 NaOH. This time there are 3, so 3 NaOH. So you will have 3 here, 3 NaCl. Again, to eliminate those, only one water molecule can be lost. So when one water molecule is gone, here you will have COOH. COOH. So this COOH is not reacted with NaHCl, it is reacted with NaCl to convert this carboxyl group also into a salt. So you will have COONA, then HCl is gone, then HCl is gone. Then in the last step, this COONA, we call this as here ONA. So this compound is reacted with the 2 molecules of HCl to give you salicylic acid, plus 2 NaCl. So this is second part of RhymerTimon reaction. You practice only for salicylaldehyde if you are appearing for theory exams. If your intention is to practice for other competitive exams also, then you need to remember RhymerTimon reaction can give you salicylaldehyde as well as salicylic acid. In order to get salicylaldehyde, you use chloroform. For salicylic acid, you need to use CCl4. Now how will you change the reaction here? 3 NaOH were there, this time 4 NaOH. Instead of chloroform, you use CCl4. The main product is salicylic acid. Now the byproduct should be 1 NaCl is also written here. Then the byproducts are once water, then twice water, 1 HCl, 2 HCl, so 2 HCl, then NaCl thrice plus twice 5 NaCl. Okay. This is RhymerTimon reaction. There are other chemical properties of phenols which are not so important, but yet we shall see those also. The next chemical property is 6th chemical property, reaction of phenol with zinc dust. This reaction is important in case you are trying conversions. How do you convert one compound into another? If such kinds of questions appear, then this reaction should be remembered. So whenever phenol is reacted or heated with zinc metal dust, when it is heated with zinc metal dust, you will get benzene, and this OH group is gone as zinc oxide. So whenever phenol is heated with zinc metal dust, benzene is obtained. The last chemical property is reaction with oxygen. In other words, simply write oxidation. How is oxidation done? For this, you take phenol and react it with chromic acid. Otherwise, sodium dichromate in presence of sulfuric acid, which is a strong oxidizing agent. In place of strong oxidizing agent, phenol gets oxidized to form para-benzoquinone, to give you para-benzoquinone as a product. So sometimes phenols remain in quinonoid forms, then its color changes to pink. Otherwise, if it is reacted with strong oxidizing agents like sodium dichromate in acidic medium, then also you will get para-benzoquinone. So this was all for today. Today you studied about physical properties and chemical properties of phenols. In our next class, we shall study about ethers. Thank you.